Today is going to be the chapter 3 to 4 video. We're going to be doing question 3. So, to start off, we're going to start off with part A, and it's going to be asking us, a cyclist is going to be going around a circular track at 10 meters per second, has a centripetal acceleration of 5 meters per second squared. And we got to find out what is the radius of that curve. So first, let's kind of diagram a little track over here to visualize. So we have a bicyclist. It's just going around this track. And they're going at 10 meters per second. And the force of their acceleration from the radius and their velocity is equal to 5.20 meters per second squared. So we know that the acceleration is going to be equal to our velocity squared over a radius. So if we want to figure out the same thing, we're just going to be flipping these things around. Pretty much just multiplying radius on each side and then dividing our acceleration. So it's going to be radius is equal to velocity squared divided by our acceleration, which is then going to be 10.0 squared, meters per second squared, all over 5.00 meters per second squared. So, real easy. Just take out your calculator. 10 squared divided by 5.00. And that's going to give us our radius of, so R is equal to 20.0 meters. So that's our answer for part A. It's going to be 20.0 meters. Now, let's move on to part B, where it's asking a different type of movement over here. So in this time, we have a race car. So, little track over here. We have a car moving around this track. And we know that it's moving at 40.0 meters per second. And we know that the entire radius of this area is going to be 265 meters. So that's when we're going to use another equation, because we know that period, pretty much the period of time that it needs to take to do one full rotation, t is equal to 2 pi r all over v. So it's just signifying that the circumference of this divided by the velocity gives you how much time it takes to go around this. So we have our velocity. So t is going to be equal to 2 pi. And we have our radius, 265 meters, all over 40.0 meters per second. So we're going to put this in our calculator again. It's going to be 2. I'm actually going to first start this off as a fraction. So 2 pi. And then 2, we'll see, radius was 265 all over 40.0. Whoops. Let me add some times in this. So I just freak out. And then we'll put that. That's just the exact form. So in our estimated amount, our time that it takes will be 41.6 seconds. And then that'll be the answer. So that'll be the period for this. All right, so moving on to part C, which part C is going to be continuing on with the race car. And now this time we're calculating what's the car's acceleration. And pretty much we're doing what we did earlier, where AC is equal to v squared over r. So we know that 40.0 squared all over 265 is equal to, let's do this, so 40.0 squared, divide that by 265, it'd be 6.03. So we'll round that over. It's 1, 2, 3, 1, 2, 3. We'll say it's 6.04 meters per second squared, and that's the acceleration. Pretty easy. All we have to do really is just follow the formula and just input values, and we'll be able to find out either the period, acceleration, or its radius. So moving on to part D. I'm gonna erase this actually. Make this part D. I'll just put part C over here, so we have more room. All right. So part D, the wheel of a stationary exercise bicycle at your gym makes one rotation in 0.670 seconds. Consider 2 points on this wheel. We have point P and we have point Q. So we have to find the speed of point P on the spinning wheel. So that'll be for part D. So we have a little bicycle wheel. Wheel over here. And we know that it is making a full rotation every 6.0 seconds, 6.70 seconds. And we have two different points here. We have P or we have Q. And P is going to be equal to 0.100 meters. Or actually, well, it's equal to centimeters, 10.0 centimeters, and then Q is equal to 20.0 centimeters. But since most of the time we're working in meters per second, we want to convert this over to 0.100 meters. And then also as well for the 20 centimeters to 0.200 meters. Just good to convert over to make sure that all the units are aligned, because if not, it would be in centimeters per second. And then you'd have to convert back to meters. So we need to figure out what is going to be the speed. So we have the time. So what we want to figure out is our velocity, which is speed. So we know that T is equal to 2 pi r over v. So we're pretty much going to be flipping this around, multiplying velocity on each side and then dividing over. So now we know that velocity is equal to 2 pi r over the period. So pretty much for v, velocity of p, it's going to be 2 pi over 0.100, which is our radius, all over 0.670 seconds. So let's input this. Again, we'll do 2 times pi times 100 all over 0.670. And then that's going to give us 0.9378. We're going to round it over meters per second. So that's going to be our velocity. And then we'll do the same thing for velocity of Q. And this will be then moving on to part E, which is then also asking for the speed of point Q. So part D was first the speed of point P, and then we'll be repeating the same step for part E, which is asking for the speed of point Q, and we're just going to be using the values of Q, which we have, which is 0.200 meters and 0.670 seconds. I'm going to go up here and edit it just to make it quicker. And then that should be that. 0.2 and 0.670. Should be 2 pi r over, do something wrong here. So let's say 1. Okay, that was okay. I think I randomly typed 1, and then it just gave me the answer 1. I got really confused. We're looking, so I was looking at this right here, and I got randomly typed 1, but we're looking at this answer right here. And when we move it over to a decimal, it gives us 1.8755, which we can round over to 1.88. We'll actually round this over to 9.38. So this could give us 1.88 meters per second. So we have both our speeds right here. Okay, so that's for part D, and then part E. Now we're going to keep using the same values over here, and we're pretty much going to be doing for part F and part G, because they're both going to be using the same values that we have right here. And they're just going to be asking what's going to be the acceleration of both points. So we know that our acceleration is equal to our velocity squared over radius. Now we already have both of our velocities solved for both of the radiuses that were given. So we're just going to plug in for each point. So for our acceleration for P, velocity is 0.938 squared all over, which was 0.100 meters. And then for our acceleration of Q is going to be 1.88 meters per second squared all over 0.200 meters. And then we're going to solve for that. So acceleration 0.938. I'm not even typing. Oopsies. 0.938 squared. Divide that by 0.100 to give us 8.79. So 8.798, which we're going to round over to 8.80 meters per second squared. And then now we're going to switch over and then input the values for Q. And we had 1.88. So we're just inputting our values onto the calculator and then just solving for it. And then this time it's going to give us 17.672. So we'll do 17.6. Actually, we'll do 17.7 meters per second squared. So then here are both our accelerations. So this is for part F and then for part G. So yeah, so 8.80 meters per second squared. And then 17.7 meters per second squared. So, and then for part H. Now this one is just simply asking us a question of the points on this wheel that we have here that's spinning around. As our distance increases, so as we go towards this way and our radius that we're measuring increases, is our speed or velocity and our acceleration going to increase. Now we see here that 0.938 is definitely going to be less than 1.88. And then the same thing is also equivalent for 8.80 is less than 17.7. So our values for P and our values for Q. So P is always going to be smaller than Q, and that's because it's less of a radius. So we have 0.1 and 0.10, or 0.1 and then 0.2. So 0.1 is less than 0.2. So as we increase what our radius is, that means that both the speed and both speed and acceleration are both going to increase at the same time. So the answer is going to be both increase. So then let's move on here. Now we're going to move on to part I. Part I. All right. So it's asking us the planet Venus, Earth, and Mars all move in approximately circular orbits around the sun. We have to use the data in the table. So let me get this table out for everyone to see. So Venus, Earth, and Mars. That's planet. And then we'll do orbital radius. And then we have orbital period. This is going to be in days. This is in meters. So it was 1.08 times 10 to the 11th. And they have 1.50 and 2.28 times 10 to the 11th times 10 to the 11th. And then our days is 225 days, 365, and 687. So this is our table right here that's provided. And we have to figure out, so pretty much, I'm going to start off with the sun over there. And we have Venus. This is marked with V. This is E. This is M. I'll be trying the whole thing, but pretty much it's just the orbital around here. As they're all orbiting around here in all their different periods. So what we first have to figure out, it's pretty much asking us here, is that we have to find the speed. So what is our velocity for all of these planets right here, the orbital radius and the period? So we know that we can find the velocity, as earlier we looked at how velocity is equal to 2 pi r over t. So we know that velocity is equal to radius over our period. But we have to first figure out our period in seconds, because how we're doing all of this is in seconds and meters per second. At least in kilometers per second. So we have to start off by first finding our period for Venus, our period for Earth, and our period for Mars. Now that's really simple because we know that 225, pretty much we just have to, if we want seconds, all we need is just convert from seconds to days, or from days to seconds, which you know that 60 seconds times 60 for the 60 minutes an hour, we know that 3,600 seconds in an hour, just times that by 24, you get 86,400 seconds per day. So it's going to be pretty simple, just doing 225, or at least just doing every single one of our day periods multiplied by that value that we got. So 86,400 seconds. Which once you multiply that, we get 1.944 times 10 to the 7th, and 3.154 times 10 to the 7th, and 5.936 times 10 to the 7th, all in seconds. So it's all going to be in seconds right there. All right. So now we're just going to take our equation right here that we have, we're just going to input that for every single one. So velocity of Venus is equal to 2 pi times our older radius, which is 1.08 times 10 to the 11th, all over our period, which is 1.944 times 10 to the 7th. Velocity of Earth, 2 pi 1.8, 1.50 times 10 to the 11th over 1. So it's 3.154 times 10 to the 7th. And then our velocity of Mars, which is 2 pi of 2.28 times 10 to the 11th, all over 5.936 times 10 to the 7th. All right. So let's see here. So I'm going to start with 2 times pi times, I'm going to put that right there, a little parentheses to kind of split. So we're going to start with 1.08, and we're going to use our value here, which actually will be like that, 10 to the 11th, close the parenthesis, all over another parenthesis of 1.944. Yeah. So make sure you have 1.944 times 10 to the 7th. Oops, make sure parentheses outside of the square, outside of the power. And then from all of that, we'll get 34,906. 34,906 meters per second. And then we're going to be doing this for all of the other ones. So we're just pretty much just be erasing the values that we already have. And it's just going to be, so our original was, okay, so this could be 1.50. And then as we move through this, period is going to be 3.154. That's going to give us 29,881 meters per second. And then again, change up our values to the period that we want, 5.936. And then go over to this right here, which is 2.28. Here we go. And then we're at 24,133 meters per second. All right. Now, all of this is asking, we have to enter the speeds of Venus, Earth, and Mars in kilometers per second. So since it's in kilometers, all we have to do is just divide every single one of these by 1,000, because 1,000 meters is 1 kilometer. So if our decimals right here, just 1, 2, 3, which gives us 34.9 kilometers per second. And then 1, 2, 3, 29 point, we can just round that, 9 meters per second. And then 1, 2, 3, 24.1 meters per kilometers. Don't forget that. Don't forget kilometers. Yeah. So this is all going to be our answer for part I. 34.9 kilometers per second, 29.9 kilometers per second, and 24.1 kilometers per second are all the velocities of every single one of the orbitals of Venus, Earth, and Mars. So that's all part I right there. And then, using all of these velocities right here, we're just going to go on to part J. And it's just asking us what is now the acceleration. And now we've done the same process on the last couple of steps. And this is just doing the same exact thing, just in a larger scale. But it's still exactly the same format. You know that acceleration is equal to velocity squared over radius. We already have our radius, and we already have our velocities. So again, we're going to list every single one. Velocity, this time it's acceleration. Acceleration of Venus is equal to our velocity, which is 34.9 kilometers per second squared. And then it's going to be centimeters per second. This is our radius. Should get it, yeah. And then 34.9 kilometers per second squared, all over our radius, which is 1.08 times 10 to the 11th. So then acceleration of Earth is equal to 29.9 kilometers per second squared over 0.0, not 1.0, but 1.50 times 10 to the 11th. And then acceleration of Mars is equal to 24.1 kilometers per second squared all over 2.28 times 10 to the 11th. So let's just get back our calculator here. We should be doing these steps. So we're going to be doing 34.9, little square there, all over, put this in parentheses right here, 1.08 times 10 to the 11th. It's going to give us a pretty large number here, 1.12. So when I'm looking at, we can run this over to 1.13 kilometers per second squared. And now bring that upwards and we'll re-input new numbers of 29.9, and then move over 1.50. Now we have 5.96 kilometers per second squared. And then move back up here. Change our value of 24.1. And then change it to 2.28. That's going to give us 2.5. Run that over 5 kilometers per second squared. Now, we just want to move this over to meters because the question is going to be asking us in meters per second. And since 1 kilometer is always just equal to 1,000, we're just looking at square meters per second. It's 5,000. Make sure I am version correctly. Per second squared, which is then going to be meter is equal to 10 to the negative 3 kilometers. So then 2.55 divided by not right thing. 2.55 divided by 10. Oops. 10 to the negative 3. So pretty much we're going to be having, so yeah, just multiplying all these by 3. So we'll have 1,000, so let me just make sure, yeah, that by that is then going to be 1,130 meters per second squared. That's going to be our first acceleration for Venus, and then same thing, we have 5,960 meters per second squared for Earth, and then 2,550 meters per second squared for Mars. And these will be all of our accelerations given to us. All right. And then part K is just going to be asking, as the size of the planet's orbits increase, do the speed and acceleration increase or decrease? Now, we see that as this grows for us and it gets bigger, we see that let's look at our speeds here. Our speeds are actually decreasing right here, because we see that 34.9 is greater than 29.9. And since these are decreasing right here, that means that our speed, as this is growing, because this is our speed from Venus to Earth, right here, 34.9 is the velocity of Venus, and then 29.9 is the velocity of Earth. As it moves farther away, the orbital grows, there is less of a speed. So it's actually decreasing. And then at the same time, we see that some of these are decreasing as well. Because although our acceleration is increasing from 1,000 to 5,000, we can see that from Venus to Earth, we can see that from Earth to Mars, it's decreasing. So overall, it's actually decreasing, because at the same time, our velocity from Venus to Mars is also decreasing. So both decrease as it grows. So both decrease as the orbital grows. Now we're going to move on. Cut this to the side over here, because this can be part L. And part L is asking us, object A is moving at a speed of v, so it's just at a velocity with a radius of r. And then object B is moving at a speed of 2v and a velocity of just r over 2. So we have to figure out what is the ratio over here. So if we're looking at, so if we can find out our ratio by t is equal to pi r over v. So we know that t of A is equal to 2 pi r over v. But t of b, since its radius is going to be r over 2, is going to be over 2 of 2v. Since their velocity and their radius are different. So when you put them over, let's say of t over a, t over b, it's going to show us t pi r over v multiplied, because as we're dividing by two different fractions at the same time, you do keep, change, and flip. So you keep it, change it to multiply. So 2v over 2 pi. And actually, since this is its own thing, I forgot to mention right here, r over 2 is part of this fraction right here. So it actually moves down to r, and the 2 moves down there. So this turns into 4v. So this is actually 4v over 2 pi r. So that cancels, and that cancels, and then the v's cancel. So now we're just left with 4. So the answer for it would be 4. That would be the ratio. Now, if we're looking at it in terms of acceleration, we know that a of c of a is equal to just v squared over r, and then a of c of b is going to be equal to 2v squared over 2r, or r over 2. So this is going to square. It's going to be 4v squared. And then since this is technically a fraction being divided by a fraction, 4v squared is then going to be cube change flipped, and it's going to be 2 over r. So we're going to be left with 8v squared over r. So now when we do both of those over each other, so a of c, a over a of c, b is equal to v squared over r, cube change flip them, multiplied by r over 8v squared. R's cancel, v squared cancels, and we're left with 1 over 8, which simplified would then be 0.125, and that's our ratio right there. And I wasn't showing that part, but right there. So that's going to be all the parts. So that's part L and part M. Part L talks about in terms of t, and then part M talks about in terms of acceleration, in terms of the period, and then in terms of a. And that's everything. Thank you very much.